A tornado forecasting index that meteorologists almost never see climb above 1 was sitting at 8 over Quebec in northern Maine. That number belongs in Oklahoma in the middle of spring tornado season. It does not belong at the latitude of Montreal in the middle of July. And that single number was only the first piece of what set up across the eastern United States over the following 10 days. One locked atmospheric pattern, one reconfiguration of the jet stream, drove 4 separate and distinct weather hazards, one after another across the country. A rare tornado outbreak in the far north, a multi-day severe weather siege walking down the east coast, record-shattering heat baking the western half of the continent, and a tropical system quietly trying to organize in the Gulf of Mexico. To understand any of these individually, you first have to understand the thing connecting all of them. This was not 4 separate weather events happening to coincide in the same week by coincidence. It was one pattern, one large-scale configuration of the atmospheric winds high above the continent, locked into a specific shape and methodically producing hazard after hazard from the same mechanism. Meteorologists call this kind of setup a dipole. On the western side of the continent, a massive dome of high pressure, a heat dome, built itself over the Great Plains and the northern Rockies and simply refused to move. On the eastern side, the jet stream sharpened into a deep trough, a southward dipping curve in the high-altitude wind flow that functioned as a storm factory sitting over the eastern half of the country. Those two features were locked together. The high to the west and the trough to the east worked as a single system, and the critical piece connecting them was what meteorologists call the northwest flow conveyor belt. On the eastern flank of that high-pressure dome, the winds at altitude turned sharply out of the northwest and accelerated into a high-speed river of air flowing from the northern Great Plains toward the northeast. That northwest flow became the engine of everything that followed. It drove storm-generating disturbances southward out of Canada into the warm, humid, unstable air sitting over the northeastern United States. It steered weekend storm complexes southeast toward the Interstate 95 corridor, and its trailing southern edge dragged a stalling front down into the Gulf of Mexico, giving a potential tropical system the warm water and time it needed to try to organize. One conveyor belt, 4 different categories of hazard, depending on where you stood relative to it. The most immediate, and in many ways, the most surprising threat came first. A strong disturbance in the jet stream, tracking across Saskatchewan and Manitoba over the preceding days and producing tornado activity there as it moved, dove its energy southeastward into the northeastern United States and southern Quebec. What it brought with it was a wind shear environment that forecasters described using words that don't normally get applied to New England in the middle of summer. Wind shear is the change in wind speed and direction as you move upward through the atmosphere. It's the ingredient that allows a thunderstorm to tilt rather than collapse on itself, which is what lets a storm survive for hours instead of minutes, and ultimately what allows a rotating core to develop inside it. The deep layer wind shear arriving over northern New England and Quebec ran above 50 knots. That figure would draw attention in the Central Plains during peak tornado season. Over Maine and Vermont in July, by the standards of the region, it's extraordinary. The reason the atmosphere could produce this comes down to the temperature structure of the air column. The front associated with the disturbance dragged cold air in at high altitude, while the surface beneath it stayed warm and humid. Cold air sitting above warm, moist air creates an extremely steep vertical temperature gradient, what meteorologists call lapse rate instability. Layer 50-plus knots of deep layer shear on top of that violent instability. And the combined environment is exactly what produces discrete, long-lived rotating supercell thunderstorms. One forecaster called the instability shear combination rocket fuel an accurate description of what the atmosphere was capable of that day. The forecast hazards read like a spring outbreak over Tornado Alley, not a July afternoon in New England. Large hail reaching baseball size, roughly 2 3/4 inches across. Destructive straight-line wind gusts potentially exceeding 75 to 80 miles per hour, hurricane-force wind coming out of a thunderstorm rather than a tropical system, and a genuine risk of several strong tornadoes rated EF2 or higher. The areas most exposed included far northern Maine, Vermont, New Hampshire, upstate New York, and across the border into southern Quebec near Montreal, Ottawa, and surrounding communities. The single number that most clearly illustrated why this was taken so seriously was the significant tornado parameter, a composite index blending atmospheric instability, deep layer shear, low-level rotation available to a storm, and the height of cloud bases. It was specifically designed to identify environments capable of producing significant tornadoes, the EF2 or stronger variety, responsible for the majority of tornado fatalities. A value of 1 is meaningful and warrants attention. Forecast models place the significant tornado parameter as high as 8 near Quebec. 8 is an exceptional value anywhere in the country. It would be a headline number over Oklahoma or Kansas at the height of spring. At the latitude of Quebec and far northern Maine, it's close to unheard of in the historical record. That single event, though, was only the opening move. The conveyor belt driving it didn't shut off overnight. It reloaded, and when it reloaded, the focus shifted southward while the duration extended from a single afternoon to the better part of 4 consecutive days. The same northwest flow pattern turned its attention to the mid-Atlantic corridor and began a sequence meteorologists described as a siege rather than a single strike. A severe weather risk was drawn covering Washington, D.C., Baltimore, Philadelphia, Raleigh, and Virginia Beach. The air mass ahead of the incoming disturbances had been loaded with heat and moisture in the days before. Heat index values near 100 degrees from the D.C. to Philadelphia corridor, while central North Carolina looked at high temperatures between 100 and 105 degrees Fahrenheit in the days immediately preceding the storm threat. That warm, deeply unstable air was the fuel. When the northwest flow disturbances arrived and organized storms into mesoscale convective systems, large and long-lived complexes of thunderstorms, the primary threat became damaging straight-line wind. Roughly 29 million people lived inside that mid-Atlantic risk area. A significant exposure for a single day of severe weather, and only the first act of the siege. The following day shifted focus toward the Midwest, with a significant severe threat across portions of Minnesota, Iowa, and Wisconsin, every hazard category on the table, but wind again the dominant concern. The day after that drove a low-pressure system into the Great Lakes region, producing another major severe weather round across the Ohio Valley and the eastern Great Lakes, with the tornado threat returning alongside wind and hail. That same day opened a southern branch of the threat extending into eastern Georgia and the Carolinas, including roughly 13.5 million people in the Charleston and Columbia area, with the threat expected to slide toward northern Florida the following day. Then came another potential roundup and down the full east coast from Alabama through New England, completing a sequence covering virtually the entire eastern half of the country across 5 consecutive days of organized severe weather potential. Beyond the severe storm threat, the same locked pattern produced a significant flooding hazard through rainfall that didn't require severe thunderstorms to be dangerous. Training thunderstorms, storms that repeatedly move over the same geographic area in sequence, like cars passing over the same section of track, threatened flash flooding across the Mississippi, Ohio, and Tennessee river valleys, where ground saturation was already elevated from previous rainfall. Hourly rainfall rates from these storms can exceed 2 inches. Flash flood guidance for significant portions of the Texas Hill Country called for 6 to 10 inches of rain in some locations, with flash flood probabilities running as high as 40% in the most exposed areas. This flooding hazard was a direct output of the same pattern driving the severe storm threat, one system expressing itself through multiple mechanisms simultaneously. The heat dome on the western side of the continent was not a side story. It was the power source making everything on the eastern side possible. The ridge of high pressure over the Intermountain West and the northern plains ran at historically exceptional intensity. Temperatures across affected areas reached 100 to 110 degrees, with some locally higher readings. Salt Lake City approached its all-time temperature record, not its record for the date in July, but the hottest temperature ever recorded there in any month of any year. Billings, Montana reached 108 degrees at the peak of the heat event. Some areas ran as much as 25 degrees above their climatological normal for the time of year. These western heat numbers matter for understanding the eastern severe weather threat for a specific physical reason. The strength of the high-pressure dome is directly proportional to the speed and organization of the northwest flow conveyor belt on its eastern side. A stronger dome means faster northwest winds at altitude on its eastern flank, which means more wind shear delivered to storms downstream, which means better organized and more dangerous storms across the east. The record heat, straining Salt Lake City and Billings and the 50-plus knots of wind shear driving the tornado threat over Quebec, were not 2 separate stories. They were 2 expressions of the same atmospheric feature, read from opposite ends. The piece of this pattern carrying the most uncertainty, but potentially the most significant long-term implications, involved the Gulf of Mexico. While the conveyor belt marched storm complexes down the east coast, the trailing edge of the entire pattern was forecast to sag southward and stall out over the Gulf by late that week. When a front stalls over warm Gulf water in the middle of summer, the atmosphere has a well-documented tendency to recycle that energy. Forecasters were watching for a process called homegrown development. Energy pinched off the tail end of the stalling front, getting cut off beneath the western ridge, lingering over warm Gulf water, and slowly organizing into a circulation. The Gulf was running very warm, providing substantial energy for any system attempting to develop over it. Early probability estimates for tropical development in the northern Gulf ran in the 20 to 30% range. Ensemble model guidance subsequently raised that estimate to 40 to 50% over a 15-day window. It's worth being precise about what was known and what wasn't at that stage. No tropical development was formally expected within the near-term window, with the caveat that the assessment could change within a day or two as the pattern evolved. The spread in model solutions for the potential Gulf system was substantial, with different ensemble members showing the system tracking into the Carolinas and Georgia, meandering along the Gulf Coast, accelerating up the eastern seaboard, or failing to consolidate over water at all. That spread reflected the atmosphere genuinely not having made the decision yet. What wasn't uncertain was the rainfall. Regardless of whether any system got named or which track it eventually took, there was significant above-normal rainfall potential across the northern Gulf Coast from Louisiana east toward the Florida Panhandle and Tampa Bay. The water was coming. The only open question was whether it arrived with a name attached. There's one more mechanism worth understanding because it connects the Gulf threat back to the continental severe weather sequence in a way that isn't immediately obvious. The same trough of northern jet stream energy driving the East Coast severe weather siege could, if it dipped far enough south, interact directly with whatever circulation was trying to develop over the Gulf. Meteorologists call this baroclinic enhancement. When a jet stream trough sweeps over a tropical or subtropical low, it can inject energy into the system and intensify it, sometimes more rapidly than sea surface temperature or moisture supply alone would support. That's why some model runs showed the potential Gulf system strengthening as it moved north toward land rather than weakening, the opposite of typical tropical system behavior over land. The same conveyor belt dropping baseball-size hail on Maine could, within the following week, reach south to grab a Gulf low and drive it toward the eastern United States with additional intensity. Or the energy could simply fail to consolidate, leaving a flooding event without a named storm. Both outcomes involve significant rainfall. The difference is in organization, intensity, and how precisely any threat can be forecast in advance. Understanding the underlying physics makes these numbers feel less abstract. A heat dome is a large, persistent area of high pressure at the upper levels of the atmosphere. When high pressure builds strongly at altitude, it causes the air beneath it to sink. Sinking air compresses and warms. That warming suppresses cloud formation and rainfall. Without clouds to reflect incoming solar radiation, and without evaporating rainfall to cool the surface through latent heat release, the surface heats up dramatically, building day after day with no relief mechanism. Temperatures climb not just to seasonal records, but to all-time records because the feedback loop has nothing to interrupt it. But the sinking air on the inside of the dome is only part of the story. What happens on its eastern flank is where the severe weather connection lives. Air flowing around the dome on its eastern side accelerates as it turns southward. The tighter the gradient between the high pressure inside the dome and the low pressure of the trough to the east, the faster that flow accelerates. The northwest flow conveyor belt calibrated directly by how strong and how deep the western heat dome has become. The population exposure across a sequence like this is worth quantifying because the numbers reflect the geographic breadth of what unfolds. Roughly 29 million people fell inside one day's mid-Atlantic severe weather risk area alone. Another day's southeast risk covering eastern Georgia and the Carolinas encompassed roughly 13.5 million additional people. Add the populations across the Ohio Valley and Great Lakes risk zones and across northern New England for the opening event, and the cumulative population potentially affected by one or more significant severe weather events across a full 10-day sequence runs into the tens of millions. That's not a regional weather story. It's a national one, and the breadth of the affected geography is a direct reflection of how large and how locked the underlying atmospheric pattern was. The flooding dimension deserves more attention than it sometimes receives when tornado and wind threats dominate the forecast conversation. Flash flooding is statistically among the most lethal weather hazards in the United States in most years, in part because people underestimate the danger of moving water and make decisions about driving through flooded roadways with fatal consequences. 2 inches of rain falling in a single hour in any urban or suburban environment will exceed the capacity of storm drains and produce street flooding that can quickly transition to dangerous conditions. The Texas Hill Country forecast of 6 to 10 inches of total rainfall was particularly notable because of the terrain. Limestone karst geology with thin soils that don't absorb rainfall efficiently. Water runs off quickly and channels into creek and river systems that can rise with extreme rapidity. The Guadalupe, Blanco, and Pedernales rivers and their tributaries have historically produced catastrophic and rapid flood events under exactly these rainfall conditions. The human health dimension of the Western Heat Dome deserves attention too, since it sometimes gets treated as background noise when tornado and storm headlines dominate coverage. Heat is among the deadliest weather phenomena in the United States by average annual fatalities. Not tornadoes, not hurricanes, not floods in most years. When cities like Salt Lake City approach all-time temperature records, those most at risk aren't primarily people caught outdoors in the afternoon. They're elderly residents in homes without adequate cooling, people experiencing homelessness who lack access to climate-controlled shelter, agricultural and outdoor laborers who can't simply stop working, and people with underlying health conditions that compromise the body's ability to thermoregulate under extreme stress. Temperatures running 25 degrees above normal across a large area for multiple consecutive days create conditions where overnight cooling, which normally lets the body recover, doesn't fully occur. When overnight lows stay above 80 degrees, the cumulative heat loading effect can produce heat-related illness even in people who feel they're managing conditions adequately during the day. Power grid stress during extreme heat events at this scale is also significant. When temperatures across a large region simultaneously spike well above seasonal norms, the surge in air conditioning demand can strain generation and transmission infrastructure, creating cascading failure risks. Power outages during a major heat event are particularly dangerous because they remove the primary protective mechanism most people rely on and disproportionately affect the same vulnerable populations already at highest risk from the heat itself. Taken together, the sequence traced back to a single root cause: one heat dome anchoring the western side of the continent, one deep trough driving the eastern side, and one conveyor belt of accelerated winds connecting them. That conveyor belt generated a rare significant tornado outbreak in the far north, a multi-day siege of damaging wind and hail down the east coast, historic heat and its associated health and infrastructure risks across the Intermountain West, and the conditions for a tropical system to try to organize in the Gulf of Mexico. 4 hazard categories, one mechanism, expressing itself differently depending on where its energy arrived. That's the anatomy of how a single atmospheric configuration can, within the span of 10 days, touch tens of millions of people across a continent in entirely different ways. For anyone in an area under an actual active watch or warning, the real-time source to check is always the National Weather Service or the Storm Prediction Center directly, not a recap like this one.